Welcome to part 2 of chapter 11. This will cover individual gas laws and then the combined gas laws. Last time we were talking about kind of general properties of gases, and we looked at pressure and volume and temperature and how they are kind of interrelated. So now in this lecture we're going to look at mathematical relationships between these variables, so pressure, volume, and temperature, and then also number of moles of gas a little bit. So in general, we have these properties of gases that we talked about last time, and they can be modeled using math. And so we will use V as volume of the gas. This is typically in liters. We can also use it in milliliters though, so either one is fine for most things. The temperature must always be in Kelvin. You don't have an option. Always, for the entire chapter, make sure that you are in Kelvin. There are no exceptions whatsoever. And then N will stand for number of moles of gas. So this is the amount. So if it's given to you in grams, most times you will convert this into moles before you actually do math. And then our pressure is for a capital P. This will typically be given in atmospheres, but depending on the equation you're using, sometimes millimeters of mercury or torr or kilopascal is fine as well. So our first law that we are going to talk about is Boyle's law. So this guy is Robert Boyle, the son of the Earl of Cork in Ireland, which is pretty cool. Anyway, he studied the relationship between pressure and volume, and he determined that pressure and volume are inversely proportional if everything else is held constant. So if we're not changing the number of moles, we're not changing the temperature, and we're just looking at pressure and volume, then what happens is if we increase the pressure, we will decrease the volume. So that's what inversely proportional means. Inversely proportional means if one goes up, the other goes down, or if one goes down, the other goes up. So if pressure, let's think about volume. If we have our gas and we, squish our gas, we change our volume so that it's smaller. Everything else is the same, but we've now put it in a smaller container. What happens then is if we have the same amount of gas, well, now those molecules are hitting the sides of the container more frequently because it's a smaller container. So they don't have as far to travel across the container. So if we have a smaller container, our number of collisions will go up, which means that pressure goes up. So he modeled this mathematically. This is his equation. This is Boyle's law. P1 V1 equals P2 V2. And again, that means, if pressure goes up, volume goes down, or if, pressure goes down, volume goes up. They are inversely proportional. Okay? So you can kind of think about this in terms of a bicycle pump. Right? So the way the bicycle pump works is if you pull it all the way up, fill it with gas, and then when you push down, so as you are pushing down, you're making the volume of your gas smaller, right? And when you make that volume of your gas smaller, now, again, there's going to be more collisions more frequently because, the walls of the container are smaller. And so when that happens, that builds up pressure. And that increase in pressure is what causes the air to then travel into your tire. So there you go. So here, the picture here with the piston, right? If we have 4 liters at 1 ATM, and then we squish our gas, we push the piston down. So instead of being 4 liters, it's now 2 liters. So we have decreased the volume. We caused the volume to go down from 4 to 2. And if you look, the pressure went up. The pressure went from 1 ATM to 2 ATM. And again, that's because it's taking less time for those molecules to get across the container. So we have more collisions happening more frequently, which will increase the pressure. So that's Boyle's law. Our next law is Charles' law. So this guy, Jacques Charles, he is a balloonist, which I think sounds like a really cool job. He also isolated boron, which is awesome, but we are talking about him today for his study on gases. And he said that if you hold the number of moles and pressure constant. So we're not going to change the number of moles. We're not going to change the pressure. Then volume and temperature are directly proportional. And directly proportional means that if one goes up, the other goes up. So if volume goes up, then temperature goes up. Or if volume goes down, then temperature goes down. Okay, so they will do the same thing. They are directly proportional. And this is like what I was talking about last time if you stuck your balloon in the freezer. But we'll talk about it. Let's say now we have a balloon and we put it in our car on a summer day in California. And so what happens when you leave this balloon in the car, right? The balloon will get very, very hot. We are having an increase in temperature. So when the balloon gets hot, those gas particles get hot, they start to move faster. And when they move faster, they're going to hit the sides of the container more frequently. This will cause increase in collisions, right, which builds up pressure inside your balloon. And since your balloon is allowed to expand, right, balloons can, get bigger and smaller, then it does to accommodate that increase in pressure. And when it does that, that makes the volume bigger. So an increase in temperature leads to more collisions, and which leads to more pressure, which leads to an increase in volume. So, always follow that train of thought. So, but what I'm trying to get at here is that an increase in volume leads to an increase in temperature, or a decrease in volume leads to a decrease in temperature, or vice versa. So they are directly proportional. So here, again, we've got our pistons, right? And so in our first one, our temperature is 200 Kelvin and our volume takes up 1 liter. So then we really ramped up the flame, and so we have increased our temperature to 400 Kelvin. So our volume went up. And again, when our temperature went up. And so when we increase our temperature, those molecules are moving faster. And when they're moving faster, they're going to make more collisions with the walls of the container. Those, increase in collisions leads to an increase in pressure. And when we build up pressure, if this piston can expand, right, if this thing can kind of go up and down by itself, an increase in pressure will lead to an increase in volume, to accommodate that increase in pressure. So for that reason, right, we have an increase in volume. So these are directly proportional. An increase in temperature leads to an increase in volume. Okay, but again, make sure that these temperatures are always in Kelvin. Gotta be in Kelvin to have this direct relationship. If we have it in Celsius, we won't see the same mathematical relationship. So be very, very careful. Always in Kelvin. Another example is, I learned this first one firsthand. I thought I would be clever. I used to drink a lot of soda in college, right? And I thought, okay, I'll just put, a 12-pack of Diet Coke in my trunk. And then I would always have it, and, I could always be caffeinated. And I don't really care if it's hot or cold. I know that's weird, but I don't really care. So one day I was driving, and I started hearing these explosions in the back of my trunk. And turns out these soda cans started exploding. And the reason for that, right, in these soda cans, we have carbon dioxide. And so what happens is on a hot day, the carbon dioxide warms up, right? An increase in temperature will lead to an increase in molecular movement, right? They're moving faster, which leads to an increase in collisions, which leads to an increase in pressure. And unlike a balloon, the soda can cannot expand. So that increase in pressure kept building up until it made the soda can expand by exploding it. It was an absolute mess to clean up. I don't recommend it. You can also see this, like I said, by putting a balloon in the freezer. If you stick the balloon in the freezer, right, the gas molecules move slower. And when they move slower, we're making less collisions with the sides of the container. And when you do that, that decreases the pressure. And if we decrease the pressure, that will cause the volume to decrease. So Charles' law. Go ahead and complete lecture worksheet problem number 9. This will give you some practice with these relationships. And then, so I would pause and then come back when you're ready. All right, we have another gas law. So we've talked about Boyle's law and we've talked about Charles' law. This one is Gay-Lussac's law, and he studied the relationship between pressure and temperature. And so again, this is if we hold the number of moles and the volume constant. So we're holding everything else constant. We're just looking at the relationship between pressure and temperature. So this is related to what we were talking about before. If we increase the temperature, then we are going to increase the pressure. Kind of like, the soda cans I was just talking about. As you increase the temperature, right, the molecules are moving faster. When they move faster, they're going to make more collisions, and that increase in collisions causes an increase in pressure. So again, these are directly proportional. If pressure goes up, then temperature goes up. If pressure goes down, then temperature goes down. They will do the same thing. Okay. So here we go. Gay-Lussac's law. If we have, a given temperature, so say 200 Kelvin, we have a pressure of 1 atm. And now, unlike last time, we will not let our piston expand. It is stuck in place. We can't change the volume. We're holding it constant. So if we don't, if we can't change the volume and we increase our temperature, then what happens? Those molecules are moving faster. And when they move faster, they're going to make more collisions. And that more collisions will end up increasing the pressure. Okay? So if it can expand, it will cause a volume increase. If it can't expand, it'll cause that pressure increase. So very similar kind of laws. Go ahead and complete lecture worksheet problem number 10, looking at the relationship between pressure and temperature, and then come back when you're ready. All right, so as you can imagine, trying to keep all of these equations straight and remembering, Boyle's law, Charles' law, Gay-Lussac's law, right? That's a lot of different laws we've got going on. And so chemists like to make their lives easy. So rather than remembering all of these individual gas laws, we just need one. So all of those laws that you were probably writing down and you were getting ready to memorize, you don't have to. The only one that you actually need to know, that you'll be required to know, is this combined gas law. I'm not going to ask you, what is Boyle's law? Like I would not ask you that. I would ask you to apply it, maybe explain the relationship between pressure and volume, but I'm not going to ask you to simply state the relationship. If we're going to use these equations mathematically, the one that is good to know is the combined gas law, because it wraps all three of those gas laws into this same equation, which is really, really awesome. And so it's P1 V1 over T1 equals P2 V2 over T2. So as long as you know this particular equation, then you don't need to memorize all of the individual ones. You totally can, knock yourself out, but this is really the only one that you need to know. And my husband, he's like, it sounded like you were saying R2D2 when I talk about chemistry. So there you go. It is not related to R2D2. The way that I remember this equation, I know that sounds silly, is that we have, pink vultures sitting on a tree. So there you go. Or you could say, Professor Verissimo sitting in a tree. However you want to remember this, maybe you want purple vultures or, pink vampires. I have no idea. But they always seem to be sitting in a tree because I can't figure out how else to put the T on the bottom. Or if you're, if you don't have a sense of humor, you can just remember P1 V1 over T1 equals P2 V2 over T2. So I'm going to show you, though, all of those gas laws that we learned before are in this equation. So if we need to, say we need to use Boyle's law, right? Boyle's law looked at the relationship between pressure and volume. So if we want to just look at the relationship between pressure and volume, then we will just get rid of the temperatures. And boom, you have Boyle's law. Say instead, we wanted to look at Charles' law. Okay, well then we'll just get rid of the pressures. There you go. And if we wanted to look at Gay-Lussac's law, we'll just get rid of the volumes, and there it is. So all of those gas laws, all of those individual gas laws are combined into this one equation that we call the combined gas law. Sometimes you may hear me refer it to as the pink vultures gas law. That's what I mean. It's technically called the combined gas law. It's just a little bit long to say it over and over again. But the combined gas law incorporates all of the pressure, volume, temperature relationships for the gases that we previously studied. It's useful for studying the effect of changes in two of these variables. So especially, like, say we're going to change the pressure and the volume at the same time, or the pressure and the temperature, or whatever the case may be, then we can see how it affects that third variable. So we can use it for just changing one variable, or when we change two variables, but in all of these, the amount of gas remains constant. So we're not changing the number of moles of gas at any time. We'll cover that in the next lecture, but we're not going to deal with that today. So here's kind of how that combined gas law shows all these individual gas laws. So that's kind of what I clicked through before, but this is your summary page if you'd like to have it. So let's go ahead and figure out how to use this. Okay, so in this first one, it says helium gas is used to inflate the abdomen during laparoscopic surgery. A sample of helium gas has a volume of 5.40 liters and a temperature of 15 degrees Celsius. What is the final volume in liters of the gas after the temperature has been increased to 42 degrees Celsius at constant pressure and amount of gas? So I'm going to show you how I would always go through this problem. When you have this type of problem, you have a lot of variables. And so what I will do first is kind of outline my variables. I'm going to have P1, V1, T1, and P2, V2, T2, right? Because we are using this equation, P1, V1 over T1 equals P2, V2 over T2. So lots of variables happening. All right, so let's go through and figure this out. Helium gas used to inflate the abdomen during laparoscopic surgery. A sample of helium has a volume of 5.40 liters. So that would be our V1. And it says a temperature of 15 degrees Celsius. But if you'll recall, we cannot use Celsius in these problems, right? We can only use Kelvin. So before we can use that, we need to convert that into Kelvin. So we'll take our 15 degrees Celsius plus 273. So that will get us 288 Kelvin. And so then we keep reading. What is the final volume? So we are looking for V2, and it's specifying that it wants it in liters of the gas after the temperature has been increased to 42 degrees Celsius. So again, we can't use degrees Celsius here, so we'll do 42 plus 273. That gets us 315 Kelvin. And it says at constant pressure and amount of gas. So the amount of gas doesn't matter because we're always going to assume that it's the same amount of gas. But constant pressure, that matters. Since it's at constant pressure, we don't need the pressures in our equation. So we're just going to go ahead and get rid of them. So our pressures don't matter at all because it's not changing. So that changes our equation too. We're just going to ditch our pressures here. Okay. So now we've got V1 over T1 equals V2 over T2. So this is Charles' law. So now we need to rearrange our equation, right? So I would always do a couple steps. 1, outline your variables. 2, rearrange your equation. I would rearrange your equation first before plugging in any numbers. I have found that people make fewer mistakes when they rearrange their equation before they plug in numbers. Just after my years of teaching, that would be my recommendation. So our first step, because you see we've got kind of a mess going on, I would always start off, if you are not mathematically inclined, I would always start off by cross multiplying. If math is your strong suit and it's like a second language to you, and you see a quicker way to rearrange these equations, there are, and you're welcome to do that. But I'm going to show the way that will, help the most people and always lead you to the right answer. So I would always start cross multiply. So when we cross multiply, we take our denominator and we multiply it by the numerator on the opposite side. And then take our denominator, multiply it by our numerator on the opposite side. So the T2 ends up being multiplied by V1. So we get V1 T2. So that's what's happening in this arrow, cross multiply. And then same thing, the T1 will end up next to the V2. So we get that. So that's what we get after cross multiplying. And then we need to get V2 by itself because that is what we are trying to solve for. So the way we need to get V2 by itself is we are going to get it away from T1. So we're going to divide by T1 on both sides. So those will cancel out. V2 is left by itself. And then I'm just going to kind of flip this around. I'm going to switch the sides just because I like to have the variable that I'm solving for on the left. If you want to leave it on the right, totally your call. So I get V2 equals V1 T2 over T1. So like I said, all I did was take that equation on the top and I just kind of switched the sides because the sides don't matter. So then we can plug in our numbers. So V1 is 5.40 liters. T2 is 315 Kelvin. T1 is 288 Kelvin. And then we can go through and we can multiply all the numbers on the top, divide by all the numbers on the bottom, and we get 5.91 liters. So there you go. There's one example problem. We have 6 example problems today. Just so you know, whenever you get the hang of it, you don't need to keep watching all of the example problems. You're more than welcome to, but if you get the hang of it, then you know you can go on and work on other things. So I'm just going to skip forward really, really quick. Oop, maybe. So here's the lecture worksheet problems that this corresponds to, right? Problems 11 to 22. And here is the homework. This actually may not be true. So go ahead and look on Canvas for when this is actually due. Don't follow that. Sorry, I forgot to change that. Make sure you go on and look and see when homework 11.2 is actually due. But make sure to always show your work. Again, if you don't show your work, you are not going to get any credit. Because I can, Google answers and look in the back of the book too, just fine. I am looking for you to actually show me that you have learned these problems. So I'm saying all of this now so that when you get the hang of these problems, you don't, have to sit through all of the rest of the lecture problems. If math is not your strong suit, I would watch every single practice problem. Like I said, there are 6 of them. And the reason that I'm doing 6 of them is that people generally struggle on this particular chapter if they are not strong at math. So know yourself, know how many you should watch to get the hang of things. So back to this. All right, here we go. Practice problem number 2. It says oxygen tanks can be dangerous if they are heated because they can explode. An oxygen tank has a pressure of 120 atms, room temperature of 25 degrees Celsius. And so we've got a bunch of stuff. Let's go ahead and start outlining our variables. So we have P1, V1, T1, P2, V2, T2. All right. It says our oxygen tank has a pressure of 120 atms. So we'll go ahead and fill that in for P1. At a room temperature of 25 degrees Celsius. Okay, so again, we can't use 25 degrees Celsius. We're going to need to convert that into Kelvin before we can use it. So we're going to add 273, which gets us 298. Oh, sorry. 298 Kelvin. That's the temperature. It says if the temperature of the gas inside the oxygen tank reaches 402 degrees Celsius. So that's going to be our T2, but again, we need to add 273 to that to change it into Kelvin. So that's going to be 675 Kelvin. It says what will be the pressure in atmospheres? So what is P2 in atms if the volume and amount of gas don't change? So we are holding volume constant. Again, we're always going to hold amount of gas constant, so that's kind of, we can disregard that, but we're holding volume constant. So we don't need these. And when we're looking, P1 V1 over T1 equals P2 V2 over T2. Since we are holding volume constant, we're just going to go ahead and get rid of our volumes in this problem. So we have P1 over T1 equals P2 over T2. So again, what I would always do first is cross multiply to get rid of those denominators. So T1 is going to get multiplied by P2, and T2 is going to get multiplied by T1. So we get P1 T2, right, following this arrow, P1 T2 equals P2, and that's going to get multiplied by T1 following that arrow. Now we need to get P2 by itself because that is what we are trying to solve for. So we're going to divide both sides by T1 so that we get it away from it, like that. So now P2 is all by itself on that side. And again, I'm going to flip this just because I like having the variable that I'm solving for on the left-hand side. So P2 is equal to P1 T2 over T1. So now that I've got it all rearranged, I can plug things in. So P1 is 120 ATMs, T2 is 675 Kelvin, and T1 is 298 Kelvin. So again, we're going to multiply all the numbers on the top, divide by all the numbers on the bottom. We will get our answer is 270 ATM. That's a really high pressure. And it says, the second part says, the oxygen tank may rupture if the pressure inside exceeds 180 ATMs. Would you expect it to rupture? So our answer is yes. 270 ATMs is way above 180. It would blow up. So moral of the story, I guess, is do not let your oxygen tank reach 402 degrees Celsius. That seems really unsafe. On to the next problem. So if you're starting to feel confident with these, what I would start doing is pause at the beginning of the problems and at least try and go through and outline your variables. Figure out what your P1, V1, T1, and P2, V2, T2 are. Like start there and then, come back and see me rearrange the equation. And again, as soon as you're starting to feel confident, maybe, pause at the beginning of the problem, try and do it, unpause, see the answer, all that good stuff. Know your strengths with math. This is a very math-heavy lecture today. So problem 3, again, so we're going to do P1, V1, T1, and P2, V2, T2. Okay. So practice problem 3 says a 25 milliliter bubble is released from a diver's air tank at a pressure of 4 ATMs and a temperature of 11 degrees Celsius. So that's all our ones, right? So our volume here is in milliliters, which is fine as long as our other volume is in milliliters. Your volumes can be in milliliters or liters as long as your units match. The math will work out just fine either way, but you can't have one in milliliters and the other one in liters. So since it says down here, what is the volume in milliliters? Since we're going to solve for it in milliliters, I'm going to go ahead and leave this one in milliliters to start with. Okay, so then we don't have to convert things. So 25 milliliters, that is our volume, is released from a diver's air tank at a pressure of 4.00 ATM. So that is up here. And a temperature of 11 degrees Celsius. So again, we can't use that in Celsius, so we're going to go ahead and add 273, which gets us to 284 Kelvin. So it says, what is the volume in milliliters? So we want our volume, and we want it in milliliters, of the bubble when it reaches the ocean surface, where the pressure is 1 ATM, and the temperature is 18 degrees Celsius. So again, can't use that. We're going to add 273, which gets us 291 Kelvin. Okay, and it says, assume the amount of gas in the bubble does not change. Cool, got it. So we've got P1 V1 over T1 equals P2 V2 over T2. So this problem is different because now we are changing two variables. We're changing the pressure and we're changing the temperature, and nothing is being held constant except for the number of moles, which we weren't accounting for in our math anyway. So we're going to go ahead and solve for V2. So again, what I would do first is cross multiply. So the T1 is going to get multiplied by P2 and V2. The T2 is going to get multiplied by P1 and V1. So we're going to get P1, V1, T2, right, following this arrow, equals P1, V1, and then, P2, V2, and then that's going to get multiplied by T1 following that arrow. So now we need to get V2 by itself. So here's V2. And to get V2 by itself, we need to get P2 and T1 away from it. So we're going to divide both sides by P2 and T1. And when we do that, the P2s cancel out, the T1s cancel out, and V2 is left by itself. And again, like I said, I'm going to flip this so that the V2 is on the left like I like. So we have V2 is equal to P1 V1 T2 over P2 T1. All right, so now we are all rearranged and we can now go through and plug numbers in. So our P1 is 4.00 ATM. Our V1 is 25.0 milliliters. Our T2 is 291 Kelvin. And then on the bottom, we have our P2, which is 1.00 ATM, and our T1, which is 284 Kelvin. So we'll multiply all the numbers on the top, divide by all the numbers on the bottom, we will get 102 milliliters. And that's your answer. All right, let's try another. So I would recommend, starting now, try to outline your variables. So pause here, try and figure out P1, V1, T1, and P2, V2, T2. And then come back when you're done. All right, so here we go. P1, V1, T1, P2, V2, T2. Okay, it says a sample of helium gas has a volume of 0.180 liters. So that will be our V1. And a pressure of 0.800 atm. And a temperature of 29 degrees Celsius. So again, we can't use that. So we're going to add 273 to that particular one. And that will get us 302 Kelvin. And then it says, what is the new temperature in degrees Celsius of the gas at a volume of 90 milliliters? So hang on here. So this is 90 milliliters, but our V1 we have in liters. So you can either make them both into milliliters or make them both into liters. It doesn't matter, but they need to match. Since I've already written down the one for liters though, I'm going to go ahead and convert this 90 milliliters into liters. So we have 90.0 milliliters, and we know there are 1,000 milliliters in 1 liter. So we can do our train track here. Go 1,000 milliliters, 1 liter. That gets us 0.090 liters. Okay, so that will be our V2. And then our P2 is a pressure of 3.20 atms. So atms match atms for our P1, so that one's all fine. All right, so now going through and solving this, we have P1 V1 over T1 equals P2 V2 over T2. We're not holding anything constant, so we need to use all of our variables. So again, the first step, what I would do is cross multiply here. So we're gonna get P1 V1 T2 equals P2 V2 T1. And then we are solving for T2. So it's right here, right? We're solving for T2. So we need to divide by anything we don't want next to it anymore. So we're going to divide by P1 and V1 to get those to cancel out. So our P1s are gone, our V1s are gone. We're just left with T2 now. So T2 is equal to P2, 3.20 atms, times V2, 0.090 liters, T1, which is 302 Kelvin, over P1, 0.800 atms, and V1, which is 0.180 liters. So we can multiply all the numbers on the top, divide by all the numbers on the bottom. That is going to get us 604 Kelvin. But if you'll recall, the problem asks for the new temperature in degrees Celsius. So we're going to take our 604 Kelvin, and we are going to subtract 273 to get us 331 degrees Celsius. So always be sure to pay attention to units and what the problem is actually asking. All right, on to the next example problem. Oh, sorry, wait. Before that, I want to make a note. Sometimes people will see that the temperature here, 29 degrees Celsius, and then they're like, it's asking for the temperature in degrees Celsius at the end, so I don't have to convert it. No, you do, because otherwise this math that we're doing here, the math won't work out if you do it in degrees Celsius, because we're adding and subtracting 273 rather than multiplying by something. So the math doesn't work if you try and do the math in degrees Celsius. So at the beginning, you need to convert it to Kelvin, do all your math, and then convert it out of Kelvin. I know it's annoying, but it gets you the right answer. All right, now on to the next problem. All right, if you're feeling confident, I would try and actually just pause here and do the problem and then see what you get. If you are not feeling confident, try to at least outline the variables and maybe rearrange the equation and then see, tune back in. So go ahead and pause here, try as far as you can get. All right, so first thing we're always going to do, P1, V1, T1, P2, V2, T2. Okay, so going through this, a gas has a volume of 675 milliliters, so that will be our V1 at 35 degrees Celsius. So again, we can't use Celsius, we're going to add 273, which gets us 308 Kelvin, and a pressure of 0.850 atms. It says, what is the new temperature in degrees Celsius when the gas has a volume of 0.315 liters? Okay, so careful, right now our volume units don't match. We were using milliliters before and we have liters now. So I'm going to take my 0.315 liters, and again we know, there are 1,000 milliliters in a liter. So we can say, okay, liters has to cancel liters. So 1 liter, 1,000 milliliters. So that is 315 milliliters for our V2. Okay. And a pressure of 802 millimeters of mercury. So again, though, if we look at our P1, we were in ATMs, so we can't use ATMs and milliliters of mercury. If you had just done all of them as millimeters of mercury, that's fine, or all of them as torr, all of them as kilopascals, all of them as ATMs, that's all fine. But we can't have one as ATM and one as millimeters of mercury. So since I've already written down the ATM one, I'm going to change this 802 millimeters of mercury into ATMs. So what we've talked about before is that 760 millimeters of mercury equal to 1 ATM. Millimeters of mercury has to cancel down into the right to millimeters of mercury, so that'll go down there. And 1 ATM will go on the top. If we multiply the top, divide the bottom, we are going to get 1.06 ATMs. So that will be our P2. All right. Now we've got all of our variables outlined. That was a lot of work. So now we can go through and rearrange our equation. So we have P1, V1 over T1 equals P2, V2 over T2. Again, first step I would always do, cross multiply. That gets us P1, V1, T2 equals P2, V2, T1. So now we are solving for T2. So we need to get T2 by itself, which means we are going to divide both sides by P1 and V1 to get them away from there. So when we do that, those cancel out. T2 is left by itself on that side, and we have T2 is equal to P2, V2, T1 over P1, V1. All right, so T2 is equal to P2, V2, T1 over P1, V1. So we can go ahead and plug things in. 1.06 ATMs. Our V2 is 315 milliliters. T1 is 308 Kelvin. let's see, and over P1, which is 0.850 ATMs, and V1, which is 675 milliliters. So if we multiply all of that out, we are going to get 179 Kelvin. So, but again, if we go and look at what the question is asking, it says, what is the temperature in degrees Celsius? So now we need to take our temperature in degrees Celsius, that 179 Kelvin, and we are going to subtract 273, which gets us 700, sorry, not 700, looking at a different thing, negative 94 degrees Celsius. So there we go. So that is our answer. That was a lot of work. We had some unit conversions, and we had to, rearrange things. One more example problem. So here we are. Again, if you are feeling confident, this is the last one. I would go ahead and give this a try, and then come back when you're ready. All right, first thing we always do, outline our variables. All right, so it says a balloon has a volume of 785 milliliters. That will be our V1. On a fall day when the temperature is 21 degrees Celsius, can't use that. I'm gonna add 273, which gets us 294 Kelvin. In the winter, the gas cools to 0 degrees Celsius, so we add 273, which gets us just 273 Kelvin. And it says, what is the new volume of the balloon? Real short problem. So if you'll notice, nothing was mentioned whatsoever about the pressures. And what that tells you is that means that the pressure is not changing. The pressure is not affecting our problem whatsoever. So we will just go ahead and get rid of it. So when we're writing out our equation, we don't need the pressures anymore. So we are just gonna ditch them. So no pressures. So we have V1 over T1 equals V2 over T2. So first step, like I always say, cross multiply. So when we cross multiply here, we're going to get V1 T2 equals V2 T1. And then we are solving for V2, so we need to divide both sides by T1 to get V2 by itself. So now, like I say, I like to, flip it. So we'll go V2 is equal to V1 T2 over T1, and we can plug things in now. Our V1 is 785 milliliters. Our T2 is 273 Kelvin. And our T1 is 294 Kelvin. So if we multiply the top, divide the bottom, we get 729 milliliters as our answer. And that's it. That's the end of the example problems. You do have lecture worksheet problems. I would go through and do all of those before trying your homework problems, because you have the answers worked out to these, where you don't have the answers, worked out homework problems.